All right, so now we're going to do problem 48. A roller coaster car has a mass of 1,200 kilograms when fully loaded with passengers. As the car passes over the top of a circular hill of radius that's 18 meters, so your R is 18, and the mass is 1,200 kilograms, and the speed is not changing, but it's changing because it actually undergoes the uniform circular motion. So even though the speed is not changing, but the direction is changing, so there's a non-zero acceleration. At the top of the hill, what are the magnitude of the normal force and the directions of the normal force on the car from the track if the car's speed is 11? And do the same thing when the velocity now becomes 14 meters per second. Okay, so when velocity is 11 meters per second, you will also find the normal force acting on the car from the track. How do we do that? So this is like a roller coaster. We all know what a roller coaster looks like. So let's say this is like that. So this is the car, okay? And it says that when the roller coaster car has a mass and the car passes the top of a circular hill and its speed is not changing. So when we look at this diagram, so this is the track and this is the car. If we look at the draw a free body diagram, we know that there's gravitational force that's pointing downward. There's a normal force that's pointing upward. Is there any other forces acting on this car? Remember, this whole thing is undergoing the uniform circular motion, so there is the centrifugal force acting on the car as well. That's why it's keeping moving in circular motion. So, in other words, at the top, it also experience a uniform circular motion. So, how do we solve the equation? Or I should say that the net force here. The net force in this direction that gives rise to the centripetal force. Okay, so in other words, the centripetal force we know that is pointing. Centripetal force is always pointing downward, so we can use the mg minus m, and that will give you the centripetal force. So you can, if you prefer to use the just use that because this is pointing downward. So you can have your mg downward minus the normal force, and the net force magnitude has to be equal to the centripetal force. So you have the mass times v squared over r. Okay, so the r we can use a capital letter. That's a radius. So let's see. Do we have enough information to find the normal force acting on the car from the track? I think we do because the mass is given. The velocity is given, and the radius is also given. So we can actually calculate our normal force. So our normal force here is just basically equal to mg, and then minus n v squared over r. So we can plug in a number. Your m is 1,200 times 9.8 minus 1,200 times the 11 squared over the radius, which is 18. And what we found is that our normal force, after you do the calculation, the normal force is 3,693 Newton. Okay, so that's your normal force. This is when the velocity is at 11 meters per second. Experience the upward normal force with that magnitude. Now let's look at the situations when the velocity changes. When the velocity changes to 14, what will happen? So you still have equations like this. You still, because the free body diagram does not change, you still have the normal force minus, you still have the mg minus normal force, and the net balance give rise to the centripetal force. So once you have that, then the only thing that you would change is just the magnitude of the velocity. So let's say your n here. So from here you have your mg minus mv squared over r. And so when you do this, now it's 14, and then your R is 18. When you do this, the normal force now is equal to negative 13.06 Newton. What does that mean? It means that when this velocity is so fast that the normal force, the normal force is actually in the opposite direction. Okay. So so it does not. So the track does not exert a normal force that's up. That is upward. It's actually exert a normal force that's downward. That's basically what it means. Okay. Now 57, the last problem from this chapter. All right, so 57, a puck of mass that's 1.5 kilograms slides in a circular of radius R, that's 20 centimeters, on the frictionless table, while attached to a hanging cylinder of mass M that's 2.5 kilograms by means of a cord that extends through a hole in the table. What speed keeps the cylinder at rest? Okay, so this is the diagram. This is the tabletop, and there's a hole there, and then there's a puck here that's making a uniform circular motion. And this is the hole, and then here you have a wave, the cylinder. So this is the capital M. So the capital N is 2.5 kilograms, and the little m here is 1.5 kilogram, and the radius is 20 centimeters. So what is the minimum, what speed of this, so that this whole thing is not moving? Which means that the net force acting on this, the whole system has to be equal to, the net force on this has to be balanced so that the whole thing would not, the cylinder is not moving. So this thing is not moving. At what speed of this part that it has to acquire so that the whole thing is not moving? So we need to draw a free body diagram for this capital M. So this is a little m here. This is the cylinder. So if this whole thing is not moving, which means that net force acting on this cylinder has to be equal to 0. And there's a tension or the core, so this have to be balanced with each other. So T has to be equal to mg, capital Mg. Okay? So now the question is, what is the T? So this is the same core. And then if you look at this, on this free body diagram, you have the downward gravitational force, you have the upward normal force. They balance each other because in the vertical direction. Now in the horizontal direction, this tension will be equal to the centripetal acceleration, centripetal force, so that the whole thing, keep it moving like this. And that tension provides the centripetal, force. So in that case, you will have what is the force for centripetal. So in other words, this tension is equal to the centripetal force. So you have your T that's also equal to little mass m, the v square, the m, and then v square over the radius r. Okay? So in other words, this tension, so this is equal to the lowercase m and then over r. So you're asked to find this capital M. So the capital M, the mass of the cylinder, is just equal to the lower, you're asked to find the velocity. So you have this. So you have the capital M, which is 2.5 times 9.8, and then that's equal to the little mass. That's 1.5 times v squared over r, and r is 0.2 meters. So your v is equal to square root of 2.5 times 9.8 times 0.2 over 1.5. So after you do the calculation, you'll get that the velocity, how fast does it have to move in order for the whole thing have the cylinder to be at rest. That will be 1.807 meter per second. Okay, so that's a simple question. This is a simple problem that dealing with the centripetal force and the tension.